Okay, this video is for AP Calculus, and we're going to talk today about integration by parts, which is one of the major procedures for doing integration. It's probably the second only to integration by substitution and just using derivative or antiderivative shortcuts. So definitely important to master this. We're going to break this video into two sections, or this lesson into two videos. In this first part, we'll focus on the main procedure. So integration by substitution is one of our main techniques for evaluating integrals, but another widely used technique is this integration by parts. The difference is that integration by substitution works whenever you have a function inside of a function, so it's the thing that corresponds to the chain rule. But integration by parts is the equivalent in the integral of the product rule for derivatives. So we can actually derive the formula for this integration by parts because to use this procedure, we have to memorize a formula by using the product rule for derivatives. So if you we know that we have two functions, let's say u and v, that are both functions of x, and they're multiplied together, like say 2x e to the x, and we want to take a derivative, we know we have to take the derivative as the first times the derivative of the second, plus the second times the derivative of the first. Right, so we can do that, and then write this derivative here as dv dx du dx here. Right? And then take an integral on both sides. And if we do that, if we take an integral on both sides here, so each of these become an integral, then this side just becomes the uv, and this side becomes the integral of u dv dx, and then an integral with respect to x, plus the integral of v du dx and an integral with respect to x. But that means that these are canceling out effectively, and you get uv is equal to the integral of u dv plus integral of v du. And then you can solve for one of these integrals. Typically we solve it for this one, and we get what we call the integration by parts formula, which is that the integral of u dv is equal to the product u times v minus the integral of v du. Right, so in order to use this, we have to have an integrand, which we can divide, and we can take part of the integrand and put it into this u function, and fold part of the integrand into this dv function. And then we're going to do something in our toolkit on the side to be able to produce the u, the v, and the du so that we can substitute in this formula. All right, so another way to derive this formula is using the idea of area under a curve. Now, we really haven't covered this in this lecture series yet, but if you've taken any previous calculus courses, you know that well, I guess we have talked about this. Yeah, in general, we have talked about this, that the area under a curve is a sum of a bunch of rectangles, and that does represent the definite integral. So yeah, so this red area, for example, this would be, let's say we have this variable u on the horizontal axis and the variable v on the vertical axis, and this little width here would be a little change in u du, and this height would be this function, except it would be the function v. So this would be v times du would be this little area, and if we sum that little rectangular area up over this function curve, we would get the red area here. On the other hand, if we kind of turned our paper sideways, this would be a little change in the v, the width dv. This height would be the u variable, so u times dv is a rectangular area that's horizontal like that, and then if we were to sum this across the vertical strips here, we would get the blue area. So the integral of u dv plus, that's the blue area, plus the integral of v du, which is the red area, has to add up to the total area, which is just u times v. And so this is kind of an informal derivation. The product rule derivation on the previous screen is the more formal derivation. But somehow we just need to memorize this. So I would just say go ahead and memorize this rather than try to derive it as you. All right. So the idea is this procedure is going to be useful when you have a more complicated integrand, where you can peel some of the integrand off and make it the u, and then the rest of the integrand is multiplied by that u. That's going to get folded into the dv, so that we can write a part of it as u and a part of it as dv. And then we'll take the derivative of the u, and we'll take the antiderivative of the dv. The derivative of u will give me the du that I need to substitute here. The antiderivative of the dv will give me the v that I substitute there, and then we've defined u, and we can substitute everything in this integral. So the idea is that it pulls some of the integrand out to a product and leaves a hopefully simpler integral that we can use shortcuts or other things like u substitution to solve. All right, so this procedure works if when you do this substitution, you get a simpler integral here to evaluate. Okay, so to see how this compares to our other main procedure, integration by substitution, we're going to do two different problems here side by side. First, let's do the one we're familiar with, which is integration by substitution. So this is the previous one. This is useful whenever we have an integral where the integrand has a function inside of a function. And so in the toolkit, we assign the inside function, in this case 3x to the letter u. We take the derivative, du dx, which gives me 3, and you multiply it out to get du is equal to 3 dx. That means that dx is 1/3 du, right? And then the idea is we're going to substitute from our toolkit here into the original integral to get something that's simpler. So this becomes an integral of e to the u, and this dx becomes a 1/3 du. And when you pull the constant outside, we now have something we can just solve with a shortcut, an antiderivative shortcut. So that's the copy plus the c, and then we can resubstitute from the toolkit to get 1/3 e to the 3x plus a c. Right? So that is how integration by substitution works. This is the inside function. And more importantly, we're substituting back into the original integral. We're substituting into the original integral. Okay, let's compare that to this new procedure for number 2, integration by parts. So what we're going to do here is define this more complicated integral, which we have things multiplied. We're going to define part of it to be u, and part of it to be the dv differential. Right, so what I'm going to do is I'm going to divide this right here. This 3x part I'm going to make u, and this e to the x times dx we're going to call dv, so that I can rewrite this as an integral of u dv. Right, so off on the side, this is the u, this is the dv, so we've got an integral of u dv. But off on the side, we're defining our u to be 3x and our dv to be e to the x dx. Okay, just like with the integration by substitution, we'll take the derivative of du, and that's so that we can get this dx. Right? Actually, it's so we can get a du, so we're doing something similar as far as substituting. So we have du dx equals 3, and that means that du is equal to 3 times dx. The difference is that we're going to eventually have to substitute that this is equal to this memorized formula, uv minus integral v du, right? So we have the u because we selected that, right? We have du now because we were able to take the derivative of the u. The last piece is we need the v to substitute here and here, and to get that, since we have dv, we will take the antiderivative in the toolkit. Right, so the toolkit now has two operations, a derivative on u to produce du, and an antiderivative on dv to produce v. In this case, the v is e to the x. Okay, so the first thing is that there are two things in the toolkit rather than one for the integration by substitution. And then the second thing is we're going to substitute all this, but we're substituting into this memorized formula instead of back into the original integral. So I'm going to write this out. It's uv minus integral v du, and then we're going to substitute 3x for the u, and we're going to substitute, let's see, this v turned out to be e to the x for the v, and then minus integral of that same v again, e to the x, and then the du, which is 3 dx. Right, so instead of substituting into the integral, we substituted into this memorized equation. Right, and then that should result in another integral, but that integral should be simpler. So let me just write this little something, 3 times x times e to the x. I'm going to pull the 3 outside here. Then we have an integral of e to the x. Okay, so this worked because we went from a form which was, ignoring the constant here, x e to the x to just e to the x. And that's substantially simpler. Now we can do the integral, which is just e to the x. We still have that uv part here, and we tack on our plus c, and we're done. That's integration by parts. Right? So the key when you might think about using this is when you have product in your integrand. You have two functions that are multiplied, which don't just include a constant, because constant can always just be moved out of the integral. So some ideas for how to choose the u and the dv. The idea is we're going to take the derivative of the u part and the antiderivative of the dv. So you should try to arrange things if you can so that those operations produce simpler things, right? Try to make sure that you take the derivative of the thing that you get u, that when you take the derivative it gets simpler, right? And then the other constraint is that whatever you put into dv, we have to have an antiderivative shortcut for, which means that logarithms, we can't go into the dv part because we don't have a memorized shortcut to do an integral of a log. But we do have a shortcut for the derivative of a log. Right. And if you happen to choose wrong, then what will happen is the new integral of u ddu will not be simpler. And then you know that that wasn't the right choice, so then you can make a different choice or try a different procedure altogether. All right, so best to see this with a bunch of examples. We'll do some examples in this first half here to give you practice. As always, you can try to practice this on your own by pausing the video and then unpause and see how you did here. Okay, so this first one, we've got integral of natural log. Now that doesn't seem like we would need to use the integration by parts because there isn't anything multiplied here. Okay, but I don't have a shortcut for natural log. So we're going to go ahead and do integration by parts. I'm going to choose a u. I'm going to choose a dv. Okay, and I can't put the natural log over here because I'd have to do an integral, which is what I'm trying to do in the first place. So instead, natural logs always go into u, well, almost always. And what that means is that the dv part is just the dx. The dx always ends up into as a part of this dv because we need it to be able to take the antiderivative. Okay, in our toolkit, we take the derivative of the u, so du dx is 1 over x. Then we multiply it out to get du, that's 1 over x times dx. And then in the dv part, we take the antiderivative. So the antiderivative over here is 1 times the constant, or times the variable v, and this one is 1 times the constant, or variable x. Right, so then we're going to substitute into this memorized pattern uv minus integral of v du. The du is natural log of x, the v is x, and we have an antiderivative of v, which is x, and then the du, which is 1 over x dx. So I'm going to move this in the front here. This is x natural log of x minus integral, but x divided by x is just a 1. So that means that that integral is x, yeah, just the antiderivative is just a constant times the variable x plus rc, and we're done. So if you did want to memorize a shortcut for the antiderivative of the natural log of x, the antiderivative of the natural log of x is x natural log of x minus x, and then plus c. Or we can just use integration by parts for that. Okay, let's take a look at another one. Again, you can pause this and try it. All right, so the correct choice here for u would be to make x the u, because the derivative of that is going to be a 1. If I put that in the other side, then the antiderivative would be 1/2 x squared, and that seems to be getting more complicated. So we will put the sign over here, okay? And then that means that I can take the derivative of du, so derivative du dx is equal to 1, and therefore du is equal to dx. And I can take the antiderivative of dv, sine of 4x dx, okay? This is the one case where I would use that, that idea that you can make the constants fix up, because the derivative of the inside is going to be 4, so the du is going to be 4 dx. I'll balance it with a 4 here, or you can do a u substitution. But this is going to end up being that the v is 1/4 times the antiderivative of sine, which is cosine of 4x. Now we're going to substitute back into uv minus integral of v du. And then the u is x, the v is 1/4 cosine 4x. And we have an integral of 1/4 cosine 4x. And then the du is dx. So this is 1/4 x cosine 4x. And I'll bring the 1/4 outside, and we have an antiderivative of cosine, You know what? I realized I made a mistake here over here. The antiderivative of sine isn't cosine, it's negative. So I need a negative there, which means that the v has a negative, which would appear here as well as here. Then plus. Sorry about that. Antiderivative of sine is cosine. The antiderivative of cosine is sine. Antiderivative of sine is negative cosine. All right, so now we got one more. Let me do that constant fix up again. So if we have a 4 dx here, and 1/4 outside there, then we've got negative 1/4 x cosine 4x, and then positive, that's 1/16. Antiderivative of sine of cosine is positive sine of 4x, and then we add our plus c, and we're done. Okay. So the right choice there would be u as x, because the derivative will make that simpler. Let's see what happens if you do choose incorrectly. Let's say that you just decided to put the sine of 4x as the u, and then you made the dv x times dx. Well, then when you take the derivative here, you would get the derivative of sine is cosine of 4x times the chain rule, so that's times 4, which means du is 4 cosine 4x dx. And on the antiderivative side, we would say that v is the antiderivative of x, which is 1/2 x squared. And then when you plug into uv minus integral of v du, the uv would be 1/2, uv would be, so you've got sine of 4x, and then times 1/2 x squared. That doesn't matter how complicated that is, because I'm not going to take an antiderivative. But over here we have v, which is 1/2 x squared, times du, which is 4 times cosine of 4x dx. Okay, so let's simplify this a little bit. We have 1/2 x squared sine 4x. That part's fine. But then we have a minus, and this is 4 divided by 2, which is 2. I'll bring that outside, and we have an x squared cosine 4x dx. So here's the problem, right? If we happen to choose incorrectly, this x sine integral becomes an x squared cosine, which means it's getting more complicated. Now, if that's happening, that just means that we've chosen those wrong. Probably we should swap those, and if we did, we would go from an x sine x to just a cosine, which is simple enough to do with a single shortcut. So that's how you can tell you've chosen u and dv correctly. If not, just choose it the other direction, or choose something else. Okay, let's do, sometimes these two techniques that we've learned, integration by substitution and integration by parts, can be done together. If I have something like this, like x sine of 4x, where inside of the sine I just have a constant times x, so that the derivative here, if I were to do a u substitution, would just be a constant derivative of 4. Then I just go ahead and go straight to integration by parts. But what if you have a case like this, where you have a cosine with an x squared inside of it, and the derivative of that is 2x? Right? So that is too complicated to jump straight into integration by parts. So instead, in those situations, we can do a u substitution first. So first, let's do a u sub. And we're going to choose u to be the inside function x squared, which means we have the derivative du dx is 2x, so du is 2x dx. And then I'm going to rearrange this so that I can get as much of this as possible in here. First of all, this cosine of x squared, actually let me rewrite this a little bit. We have a cosine of x squared, right? We have 2 times an x, well, if I could get 2x dx, that would be du, so let's do that. There would be an x squared left. Let's leave the x squared over there, and we'll bring one of the x's over here. I'm just rearranging the order here. So I have 2 of these x's, I have the 2 and the other x and the dx, and I have cosine. That way I can see that this is going to be, this x squared becomes u. If I substitute for my toolkit, this becomes cosine of u, and then the 2x dx becomes the du. All right, so now It looks much simpler, but still not simple enough because we have two things that are multiplied. So what I would do next is I would define a new letter because I like to reuse u for integration by substitution. So now I'm going to define another letter. Let's call it W. No, let's call it Y. Let's call it Y. Y is going to be U. So that I can just rewrite this as Y cosine of Y dy. Okay? Now I'm going to do integration by parts. And in integration by parts here, I'm going to define U to be the Y. I'm going to define the dv to be the cosine of Y dy. And then I'm going to take the derivative here, which would be du dy. That's 1. So du equals dy. And over here, I'm going to take the antiderivative, cosine of Y dy. So that means v is going to be the antiderivative of cosine, which is sine of y. And then I'm going to plug into uv minus integral v du. The u is y. The v is sine of y. And then I have an integral of that v again, which is sine of y. And then the du is dy. Okay, so I have one last integral to go here. Antiderivative of sine is negative cosine, so I'll make that plus cosine, and we'll put our plus c on here. And then we'll do one other thing. We'll go back through the substitution. Y's are actually u's, but u's are x squareds, which means every y gets replaced with x squared. So if I go backwards twice through this, y is u, but u is x squared. So this is x squared sine of x squared plus cosine of x squared, and then plus that c. And that's the final answer there. Right, so whenever you have something that is multiplied, it suggests we're going to use integration by parts. But if the integrand of one of these has an inside function, or the argument for one of these functions has an inside function that's more complicated than just x or a constant times x, we might want to do a use substitution first before we do integration by parts like this. Okay, let's do, let's see, actually, I think this, let me save, yeah. We're going to save this one for, no, we're going to do this, yeah. We're going to do this. This will be the last example for the first part video. Sometimes you do need to use integration by parts more than once. So let's go ahead and do a u substitution where u is x squared. That means the dv here will be sine of x dx. So the derivative du dx is 2x, and we get du is 2x dx. And the antiderivative of sine is negative cosine, so v is negative cosine of x. And then we substitute into uv minus integral v du. The uv is x squared times negative cosine x, and then minus an integral of negative cosine x times 2x, make that a little clearer, negative cosine of x times 2x dx. So cleaning this up a little bit, negative x squared cosine of x. Negative negative is plus. I'm going to bring this 2 outside, and then we have x cosine x. Right, which is not yet simple enough to do with a shortcut because I have two things multiplied. So what's going to happen in that case is I'm going to do use substitution, integration by parts a second time. What I like to do is put a bracket around this integral and then just do the integral over again as a separate problem. So now the u is going to be just x. The dv is going to be the cosine of x dx. We take the derivative du dx, and we get 1. So the derivative du is equal to dx, and we take the antiderivative here to get that v is just sine of x. And then I'm going to, in this parentheses, put a uv minus integral v du. Right? And that's still going to be multiplied by all this other stuff, but let's just keep going here. This is x times sine x minus the integral of sine x dx. So that is x sine x minus the antiderivative of sine is negative cosine, so this becomes plus cosine of x. Okay, then I'm going to put the 2 here and the rest uv from the original, and then we'll tack on our c, right? So you can do an integration by parts and then still need to do another integration, which means that if you wanted to distribute this final answer would be negative x squared cosine x plus 2x sine x plus 2 cosine x's plus a c. And this is really typical for a form. We have something that starts out pretty complicated, like a term with x squared cosine, and then the x times the trig function, and then just the trig function, and then just the constant. Okay, so that will be it for the first part of the video. We'll do a second part for the remaining examples.